Okay, this is problem number 4 on the section 4.2. It's a regression problem. Here we're trying to relate the number of days absent from class and the final exam score. Okay, so we use StatCrunch to get this first regression line. I've got other videos on that, so I want to spend this video focusing more on the interpretation side of things. So we're asked in part B to interpret the slope and the y-intercept if appropriate. Okay, and we've got these different choices. I want to show you how I do that. So here's the regression line equation. Now, of course, the slope is just a number in front of x, right? So this negative 2.765. The y-intercept is this 88.461. We'll deal with that in a second. Now, the first thing to note is that any number, it doesn't matter if it's this number or anything, but any number can just be written as itself over 1, right? 'Cause dividing by 1, it doesn't do anything to a number. Okay, we'll come back to that in a second and what that means. But let's go here to the basic kind of elementary algebra definition of slope. Slope is equal to the rise over the run. Sometimes we say the change in y's over the change in x's. So how much do the y's change as we change in the x's? So another way to say this or update this kind of definition for regression is the change in the response variable over the change in the explanatory variable. Now, of course, in this situation, our response variable ends up being the final exam scores. So the top really is the change in the final exam scores, and then the bottom is the change in the explanatory variable or the change in absences. So the slope is equal to this fraction right here. The slope is equal to negative 2.765 over 1. So this is going to be the change in our final exam scores for every additional absence, right? Every time we have one more absence, we're going to drop this much in our final exam scores, about almost 3 points. Okay. And this is just how we say that in English. On average, right? This is on average because the regression line is just the best fit line for the data points, right? A lot of times it doesn't go through any of the data points. It doesn't even touch any of them. So it's not like if you pick any two data points, they're going to have, those 2 points are going to give you the same rise and run as what we're talking about here. But on average, right, for the data as a whole, the student's final exam score drops by 2.765 for each additional absence, right? For each one additional absence, we get this kind of drop, okay? So we go back to the question, and that's this right here. For every additional absence, the student's final exam drops 2.765 points on average. Okay, now we're going to look at the y-intercept, which is the second number right in the regression line, the one without the variable next to it. And we know that the y-intercept is on the y-axis, right? It's where the regression line crosses the y-axis. So think about the coordinates of that for just a second. It's some x coordinate, and the y is 88.461. Well, since this is on the y-axis, we actually know what this question mark is, right? It's got to be 0. Because if it was anything other than 0, if it was anything positive, it's going to be, this point is going to be over here somewhere on this side of the y-axis. And if it's negative, it's going to be somewhere over here on this side of the y-axis. Okay, so the x-coordinate has to be 0. So really, this y-intercept is a point 0, 88.461. But what does that mean in terms of our model, in terms of our regression line? Sorry, I have a little typo here. This should be the model or line predicts an x of 0 gives you a y of 88.461. Okay, an x of 0 gives you this 88 number. Okay, now let's start translating that into the language of regression, right? An explanatory variable of 0 gives you a response variable of 88.461. Okay, and to take that into our specific model, right? 0 absences result in a final grade of 88.461 because the explanatory variable is really absences, and I should have response variable here instead of y. The response variable here is the final grade. Okay, so Yeah, what that means, going back to, let's see, go back to our question, that the final exam score of students who miss no classes, right? 0 is the number of absences, so you're missing no classes, is predicted to be 88.462 on average. Okay. Now, I got a quick note here. You can sometimes get different kinds of answers for this. Sometimes you can't interpret the y-intercept. In this case, you could. This happens when an explanatory variable of 0 doesn't make sense. So sometimes, like if you were doing two things, like the cost of a house, and that was the response variable, and the explanatory variable one was square feet. So of course, the bigger the square feet of a house is, the higher the price is, and you can capture that with a regression line. But if we wanted to talk about the y-intercept of that regression line, then we're talking about 0 square feet. Okay, so there's really no houses that have 0 square feet. In this model, having a 0 is okay, but it doesn't make any sense to talk about negative, right? Negative absences. Like what would it be to miss -2 classes a semester? Okay, so even though the mathematical line goes on forever, right, there's a point at which it doesn't make sense anymore for the real world phenomena that it's modeling. Okay, sometimes 0 makes sense and sometimes it doesn't. Okay, in this particular problem, it makes sense. Okay, so part C is to predict the final exam score of a student who misses 5 classes. So that's the whole value of having a regression line, right? Getting this regression line is it allows you to make predictions, intelligent predictions about, what somebody who misses 5 classes will get as a final grade. And so we do that. The final grade's the Y, right? And someone that misses 5 classes, the 5 classes are X's, right? Because absences are X's. They're the explanatory variable. And we can just use the regression equation by plugging in a 5 for an X, okay? And then just working it down. So if I plug in 5 and I do the math, I get 74.636, and I think it wants us to round to 2 places. So rounded, that's 74.64. Okay, just check it real quick. Make sure. Okay, good. Okay, now compute the residual. Now, what's the residual, right? The residual is really the difference of the observed value at 5 and what we predicted to be at 5. Okay, so remember, we have actual data. And in fact, we even have a data point where somebody missed 5 times, right? Number of absences. So somebody missed 5 times and they got a 74.2. Now this is an actual data point. Remember, the regression line doesn't have to run through the actual data points, right? It's the best fit line for all the data points together. So there could be some difference in what we predict and what we actually see here for this final exam score with this data point, okay? So that's the residual. So we just take the observed value, or 74.2, right? Which is what we observe. If we have 5 absences for this data point, we observe 74.2, right? And the predicted value, right, which was what we got by plugging in 5 to our regression equation and then just subtracting them. So we get negative 0.44, which is, it's about a half a grade off, right? And since it's negative, right, let me put this in first. So negative 0.44. And since it's negative, the final exam score, the observed one is below the average, right? Our prediction's a little higher than the actual observed, right? Our predictions are just a little bit higher than this number, than this observed data point. It could be higher, for a different problem. But in this one, it's below. Okay, now it wants us to draw, see these different scatter plots and figure out which one is ours. This is actually really easy in the sense that you can tell here by the regression lines. There's going to be different clues for different problems as to what But like you can tell this regression line doesn't seem to have anything to do with a best fit line on the exam scores versus absences, right? It just kind of goes from 0 to 1 point, right? Also, this one right here is not even a line. This is just kind of a scatter plot where you connect the dots. So you've got this jaggedy line, right? The regression always produces a line. So it's really between these two right here. And I'm going to say it's not this one because this line looks totally flat. And what do we know about our line? It has a negative slope. If I look back up here, it's got a negative slope. So it should be sloping down from left to right. So it's a pretty easy process of elimination for this one. Okay, continue. Okay, now would it be reasonable to use the least squares regression line to predict the final exam score for a student who had missed 15 class periods? Why or why not? Okay, so I'm going to take you back to my work and talk about something called scope of the model, which I can't quite fit in this picture. Okay, there we go. So what happens, there's areas where the regression line is totally not interpretable. Like we talked about for this one, it doesn't make sense to have any negative absences. So, it also wouldn't make sense to talk about after this line crosses the x-axis, because any x values out there are going to produce negative final exam results, which, no teacher would give you unless they're really evil, right? Everybody, no matter how bad you do, you can't do worse than a 0 on a final exam. Okay. So, but there's an additional thing called the scope of the model, where the regression line gives you good predictions around where the data points it has are. So for these values right here, the regression line is going to give you a pretty good prediction about where what the y value should be. Okay, if you plug in any of these x values, it should give us a pretty intelligent guess about what the y value would. That's because we have data points here. Okay, but what happens is areas where there's no data, but the line still continues, the predictions aren't as good. The model is much better when it has data around the prediction that you're trying to make. So areas over here where there's no dots, right? If I plug in any of these x's, even though they're positive and they definitely have an interpretation, the model won't fit it very well. Okay, we have no confidence that the model is going to do well in these areas. So that's what's called the scope of the model. And if you look at it, none of here's our scatter plot. We don't have any data points out near 15. So that's like 50% more than our mid value, right? So that would be kind of way out here if I continued the graph. There's no real data points around that. So I can't be very confident that my model is going to predict that well, because it's outside what we call the scope. So no, because no, because 15 absences is outside the scope of the model is the right answer here. I hope that makes sense. Okay, I hope that helped on this problem.